So hello there. This is lesson 2. You remember we started, of course, in this lesson, let's do on the discussion of the mole. Okay. Previously, if you haven't reviewed lesson one, which we covered, you can find it where you found this one previously. I think we covered what is more, what is more. We covered the Avogadro's number, the 6.0 times 10 to the power 23. Then I think we found that for basic elements, especially metals, if you take its relative formula mass, you convert that one in gram, you find that you get what is called the molar mass for that particular product. Remember, we say the sodium is number 11 on the periodic table. Therefore, it has the 11 protons, 11 electrons, and some neutrons there, and has a mass number of 23. And this mass number of 23 is the relative atomic mass 23. And then when you take this 23 in grams, 23 grams, count the number of particles which are there, you find it has that number of particles, or in this case, atoms of sodium. And we said this is now equivalent to 1 mole of sodium, and we went ahead to do some bit of mathematics related to this. The other things which we also covered quite comprehensively related to that is the molar mass, or the molar the molar mass when it relates to the gases. And we said we have to be a little bit careful, because if we considered something like, let's say, nitrogen N2, we found that if we were to take 1 mole of nitrogen, it must contain 6.0 times 10 to the power 23 particles of nitrogen gas, but in this case, nitrogen molecules. This is very key, not nitrogen atoms, but nitrogen molecules. And we said because of that, because each molecule has 2 nitrogen atoms, and we know that the mass of sodium is 14, then the relative, not relative, but the relative formula mass or molecular mass of sodium, and not sodium but nitrogen gas, will be equivalent to 14 times 2, which became something like 28. Because we are dealing with the mass, we came to grams as such. So have a review of the previous chapter. If you are able to view that lesson, it will give you a better edge to understand what we are going to chat about on this follow-up topic of same molar calculations. Okay. I'm trying to pick a good pen. We have a good sized. See this one? Yeah, I think this one should be sharp enough. Should be sharp enough. So it's still too thin. Yeah, we'll go with that one. Okay. Right? So I want us to discuss a bit about the moles of compounds, which of course we have already started, because when we were talking about something like carbon dioxide, that's already a compound. When we were talking about the water molecule, that's already a compound, only that these compounds were in terms of gases. But let's consider, for example, when magnesium reacts with the oxygen gas to form magnesium oxide, like that. So if you consider magnesium oxide, this product which has been formed here, we can say it is one magnesium which has combined with one oxygen atom. You remember about the valence, because when we are dealing with the compounds, the, 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 the what do you call it? the structural formula or this equation, the equation of the compound must be very, very right. Otherwise, you get the wrong calculation when you do what? When you go to do your calculations. I'm going back to remind you that you remember magnesium is a metal which usually has a valency of 2 during the reaction. Oxygen has a valency of 1 during reaction, and you used to exchange them like that so that you would get magnesium. It would appear like it is magnesium 2, oxygen 2, but because you want to leave it in its simplest form, we write magnesium oxide as exactly like that. So, but that is another chapter altogether, or another of writing chemical equations and balancing them. Have a review at our smart SmartMe.Africa site. You should be able to see some lessons there related to the general chemistry for the rest of the subject. Today we concentrate, or in these lessons we concentrate on the molar. So we assume by default that you know when we are writing the magnesium oxide or any other formula, you will be requested to write it, that you know how to write it. So this is magnesium. This one tells me that in this particular one atom of this one, I have one atom of magnesium combined with one atom of oxygen. And I know that I'm about to calculate its formula mass. I know that the formula mass for magnesium should be, is it 24? Whereas that one for oxygen should be 16. Okay, just to clarify that. So these masses, usually most of the time you'll be given in a periodic table. So magnesium is 24 right there. Oxygen, of course, is 16. So that's okay. At least oxygen we have dealt with it many times. So the formula mass will be 24 plus 16, which gives me 40 grams. So this one tells me that if I take 40 grams of magnesium oxide, the magnesium oxide, of course, is obtained by you burning magnesium strip, which is a yellow, not a yellowish, but a shiny silver metal in the presence of oxygen, which burns with a very bright white flame, and it produces a white product. That white product is essentially magnesium oxide. Okay, so I'm saying if I take 40 grams of magnesium oxide, this one, when I go inside an account, I'll find it should contain 6.0 times 10 to power 23 these particles of magnesium oxide, okay, of that compound magnesium oxide, because we are talking in terms of more. So the same thing which we are talking previously, it's the same thing we are talking about here. It's not anything different. Suppose I take something like calcium chloride. It's that's the formula of calcium chloride. Again, I come and try to calculate its molar mass. I'll find the RFM for calcium, or RAM for calcium, is 40. RAM for chlorine is at 5.5. Okay, that one again you can easily get it from the periodic table. So when we come to find the relative formula mass, we are going to get that 5.5 times this 0.5 times 2, because we have two chlorine atoms there. Okay, 40 is for calcium. We add that 5.5 times 2, and this one will give me 40 plus is this one 71? I think 71, and this one will give me something like 101. 111. It's actually 111 grams. Now, this is what will tell me that 100 grams of calcium chloride is equivalent, or is the same as 1 mole of calcium chloride. All right. So then when we know this, we can do the calculations just previously as we were doing. Suppose I'm given something like 50 grams of calcium chloride. All right, how many moles are here? How many moles are there. And then I will put it in multiples. How many moles? That's number one. Number two, how many atoms of calcium, and how many atoms of chlorine, Cl, not chlorine gas, but chlorine. All right. So let's try and work out that one. Let's try and quickly work out that one. So if I have taking a green pen there, if I have 50 grams, first of all, I start with what I know. I know that 111 grams, 111 grams is equal to 1 mole and is equals to is equals to 1 mole. 1 mole, that is enough. If I have 50 grams, how many moles are there? Okay, so and I put my x there. Do cross multiplication as usual. I told you that you don't need to remember anything, which will give me 111 gram dot x is equals to 50 gram dot 1 mole. Okay, I divided. Trying to make the x the subject of a formula, dividing by 111 by 111 gram on both sides. That one goes, and then gram goes. So I'm left with 50 over 11. Let me try and work out this one to two decimal places using my calculator. It's 50 divided by 111. And this one gives us at 0.45. 0.45 more, 0.45 moles. All right, so that's the answer to the first part of the question. That one we have it in black and white or black and green as you would like it. Yeah. Now, how many atoms of calcium? Now here, you remember yesterday, not yesterday, previously when we were reviewing the other lesson, I said because I know the grams, I want to avoid using the calculated volume or the calculated mass or the calculated values to avoid the propagation of error unless it is absolutely necessary or unless the equation the way it has been structured or the equation the way it has been structured requires you to do so. So here, when I'm calculating the how many atoms of calcium are there, what I will do is that I'll come and say that I know from this formula of calcium chloride, it means the combination is one calcium atom combining with two chlorine I mean atoms. So no, this two shouldn't be here with the two chlorines like that. So it tells me for every calcium chloride I call it compound or allow me to call it molecule for the ease of talking. For every one molecule of this, inside it I have one calcium and two chlorides. So if I know how many of this I do have, then I know how many calciums that I have in there. So I will say this that I know that in 111 grams, I must have 6.0 times 10 to power 23 molecules of calcium chloride because this is the molar mass. Then what about 50 grams? How many molecules of calcium chloride do I have? Same cross multiplication in there, and I'll find that 111 GX, maybe avoiding writing it, is equals to 50 multiplied by 6.0 times 10 to power 23. I divide by 111, I divide by 111 so that I get my x being the subject there. Of course, you can see here calculation of the more I told you, it will always be there. These items here, it's always implied. So in this case, if we try to work out this one with our calculator, this one will give us clear this one for us. Give us 550 times 50 times 6 is 300 divided by 111, and this one will give me what? 2.7. I can take it as that 2.7 times. So the answers here, the answer here becomes 2.7 times 10 to the power 23. These are calcium chloride. Cl2, right? Then we come here. What did we know? We knew that the ratio goes like clean up a bit. I need to clean up a bit so that I have some space to write on. Okay. We know that we know that in one calcium chloride, I have I have one calcium. So in no, in 2.7 times 10 to the power 23 calcium chlorides, I should have 2.7 times 10 to the power 23 calciums, because they are going in the ratio of 1:1, right? Higher. Then we do this. In one calcium chloride molecule, I have two chlorines. So in 2.7 times 10 to the power 23, I have how many chlorines? I have 2 multiplied by 2.7 times 10 to the power 23 chlorines. And this one will give us 5, is it 5.4 times 10 to the power 23 chlorine atoms, right? Okay, and I think that was that question there. Was there any other question in there? No. What else can be asked there is that uh, what is the mass of calcium? We knew this. We knew we have 50 grams. Comment. We have 50 grams of calcium chloride. All right. What is the mass of calcium here? What is the mass of chloride in there? All right. So how are you going to handle this one? We are going to say that we know that these guys they combine in the same ratio calcium, and then two chlorides in that ratio. Cl 2Cl, one calcium, two chlorides. Okay, so and then we did find the number of moles. We did find the number of moles, which we found it is 50 grams over 111, which I have rubbed myself and I didn't record it elsewhere. So we can quickly get it here. We get it here. 50 divided by 1.45. We found we have point 0.45 moles. Okay. Uh-huh. Okay. So we are going to find is what we are going to find is what is that if we have 0.45 moles, what these masses in which ratio are going to find it means that calcium will provide 0.45 because moles they go into one into two. It's okay. It's okay. So how am I going to say this? How am I going to say this? I'm saying these are contributing 1 mole of calcium and 2 mole of chlorides. Okay, I'm losing myself here a bit, but what will happen at the end of the day will be this. If I want to know to get how it will be here, it will be that if this is calcium chloride, it's being constructed by one calcium and two chlorides. If I have this is 1 mole, 1 mole, 2 mole. For example, if I have 0.45 mole of calcium chloride, it will be made by 0.45 mole of calcium and 2 into 0.45 mole of chlorine, and this one will tell me the number of grams of calcium. Calcium in grams will be 0.45 multiplied by the mass of calcium, and this one should be give us something like what? 45 times quickly there, 45 times 40 0.45 times 40, it will give me 18 grams. So here I'll have 18 grams of calcium. Come on, give me 18 grams of calcium. What about here? I'll have this is 0.9. I'm talking about the chlorine is 0.9. This time still 0.9 of that 5.5. That 5.5 is the RFM for the relative formula mass for chlorine. Chlorine atom is it 5.5? Let's find out, but I believe that should be it. Yeah, it's 35.5. So in our book here, so we are multiplying that 5.5 by 0.9. We do 35.5 multiplied by 0.9. This one will give us what 39, that 1.95, which if you approximate, where's my pen? 30, that what? That 1.95, which is approximately that 2 grams. So, and you see, if you add those two components there, you see that they add up to the 50 grams. Here's my pen, 50 grams, which we started with at the beginning. Okay, we'll do another one like that so as to be in a better position to get how those problems are going. Yeah, consider something like the fertilizer. You know this one, ammonium fertilizer is ammonium nitrate of 3. This is the regular fertilizer, the top dressing, which you find your parents using during the top dressing activity. It is made up of 2 nitrogens, 2N plus 4 hydrogen, 4H plus 3 oxygen. Okay, is that true? 2N plus 4 hydrogens and 3 oxygens. So if we are going to do this nitrogen, its RAN is 14, and then hydrogen is 1, oxygen is 16. All right. So moving forward, what do we find? We find this one gives us 28 plus 4 plus this should be 48. So this one gives us 32. This one gives us 80 grams. So this one tells me that 1 mole of this nitrogen based fertilizer, ammonium nitrate fertilizer, is equivalent to 80 grams. All right. And if I know that, now I can come and possibly try a nice one I find for myself. Mass of each kind of atoms, atoms in 50 kg of fertilizer. Okay, so I'm saying if I have 50 kg of ammonium nitrate, 50 kg sack of ammonium nitrate fertilizer, how am I going to, how are they going to be constructed? And the reason why we needed to know this is because these things, they are expensive for you to get to separate nitrogen the air to get that nitrogen, you need to do a lot of work, cool it, put it under pressure so that it becomes liquid, the whole air becomes liquid when you start the fractional distillation and all. The same with hydrogen, if you are getting it from water, in that the process takes power. So when we are making this fertilizer, or when these factories are making this fertilizer, they needed to know exactly how many kg of nitrogen they needed to push in there, and the exact amount of hydrogen they need to push in there, the exact amount of oxygen they need to push in there, so that the reaction is has as little wastage as possible. So in this case, we already know that its formula mass is what is 80 grams. Okay, if you know that its formula mass is 80 grams, uh, what we are going to do is to find the mass of each particle. But the best way to go about this one is not especially the way we did it previously, and that's why it complicated a bit. The best way for us to do is first of all we find what is called the percentage composition of a compound. Okay, and that's exactly what we are going to start by doing. So at least we have already calculated this one. We'll keep it on the side because we will know about it. We know it. Let me put it there on the corner. Then so that I can clean here. So what I want to do is to find out that in this compound ammonium nitrate, what is the percentage of nitrogen in it? What is the percentage of hydrogen in it? What is the percentage of oxygen in it? So again, the formula is NH4NO3. Okay, so and we already calculated the mass of is 80. So in this one, we said we have two n's, an n and n. We have 4H, and we have 3O, three oxygens, 2N, one hydrogen. So this the mass of this one is 2 multiplied by 14, which gives us 24 grams. The mass of this one is 4 multiplied by 1, because the hydrogen, the RAM, or relative atomic mass, is 1, and we get 4 grams. And then 3 oxygens, we said, is 3 multiplied by 16, which gives us 48 grams. So when we want to find the percentage of nitrogen in that compound, we are going to be finding that it's 24 over the possible 80 gram, which is this amount, the relative formula mass, the formula mass there, multiplied by 100. Okay, the percentage concentration or the percentage composition of hydrogen in that compound is 4 over 80 times 100. The percentage composition of oxygen in that one, in the same compound, it's 48, that 48 there, over 80 gram times 100. Okay, and here is a basic calculation by 810 by 83, cancel there, and then you get 30%. Okay, I cancel there and there, by 4 1, by 4 2, by 2 1, by 2 5, and I get 5%. By 8 10, by 8 6, I cut that one, by 10 1, by 10 there 10, so I get 60%. And this is wrong. This is wrong because it doesn't add up to 100%. If you find it's not adding up to 100%, then it means it is wrong. We did a mistake somewhere. And so help me. What's the problem? What's the problem? This mathematics is too simple. No problem with it. It means problem must be here by 16, 48, 4. 24. Yes, this is 28 grams, not 24. Sorry about that. So here we are talking of 28 over 80 times 100. So this one cannot be this one. So let's write here 28 over 80 times 100 by 10 by 10 by 2 by 4, 2 by 4 is 7 by 7, by 2, 1 by 2, 5, and this one becomes 35%. So this one is supposed to be 35%. Now it is able to add up for me to 100%. That's one of the control mechanisms you use if it isn't headed to where you are going, or, or you want it to head, then you know you have a problem. So having done that, from here now I'm able to tell that if I'm going to make either I'm making 150 kg of fertilizer, I need to push in nitrogen 35%, hydrogen 5%, oxygen is 60%. Okay, and if I put them in that ratio, then nothing is going to be wasted or lost. Okay, remember there. I think a little bit moment we will come to limiting reactants, and when you limit one thing, if you put less oxygen than the quantity which is required, then the reaction does not complete. Let's first of all find out in 50 kg how does this mathematics look like. Yeah, so if we are looking at 50 kg of our fertilizer, in it, you'll find how much nitrogen is there. It will be 35 over 100 of the 50 kg. Okay, hydrogen, how much will be there? It will be 5 over 100 of the 50 kg. In oxygen, how much will be there? Will be 60 over 100 of 50 kg. So this one will be by 51 by 52 by 21 by 2 is 30. So we are getting 30 kg. 2, 5 over 2, this is 2.5 kg of hydrogen. By 5 1 by 5 2 by 2 1 by 2 is 17.5, I think. So 17.5 kg of nitrogen. So if you add these three, they should add up to 50 kg, which is this plus this is 20 plus that 30, it becomes 50 kg. Okay, so this means that if I'm going to make 50 kg of ammonium nitrate fertilizer, I need to react 17.5 kg of nitrogen, 2.5 kg of hydrogen, and 30 kg of oxygen, and that combination will give me a 50 kg fertilizer. Now, this is what I was saying. If you put, let's say, you intend to put to get 50 kg of fertilizer, then you push in 20 kg 20 kg of nitrogen, 2.5 kg of hydrogen, 30 kg of oxygen. The extra 2.5 kg of nitrogen, they are wastage because they won't be used. Why? Because there are no hydrogen and oxygen molecules to react with. So it goes to waste, it becomes vapor and you can't get it back. Okay. Similarly, if you put less, let's say we needed to put 17.5, but we put 15 kg of nitrogen, but we put 2.5 kg of hydrogen, 30 kg of oxygen. Again, you'll be wasting some oxygen and some hydrogen and some oxygen, because 15 kg of nitrogen will never react complete 2.5 kg of hydrogen, will never completely react 30 kg of oxygen, and in which case that particular compound, like if you put less, the compound is called said to be the limiting factor in the chemical reaction, but we'll be going to coming to that some moments later. So I hope we are together so far. We are together so far. I want to use the same percentage composition to work out another compound like let's say sodium hydroxide. Consider this this compound here, sodium hydroxide. Okay, this one it tells me it's made up of one sodium combined with one hydrogen, one oxygen, and one hydrogen. Okay, and I know that sodium has RAM of 23 grams or molar mass of 23, oxygen molar mass 16, hydrogen molar mass 1. This one gives me 40 grams, isn't it? Yeah, 23.17. This tells me that the percentage composition of sodium percentage composition is on this product, it is 23 over 40 times 100. Okay, the oxygen, the percentage composition there, it is 16, that's 16 over 40 times 100. The hydrogen, the percentage composition is 1 over 40 times 100. Okay, and again, using our calculators here, I hope, I don't know what's the regulation. You need to find out before you'll be allowed to go in with a calculator. If not, use your mathematical tables to do this multiplication. Make sure you get them right. Remember, I said don't let your arithmetic weakness fail you when you know what you need to do. Did I see 57.5? 57.5. Let's see 57.5%. 57.5%. Okay, 16 over 40. This one is we can do some manual calculation by 8, 2 by 8, 5 by 5, 1 by 5, 20. It says 40%. 40 by 10, 1 by 10 by 2 by 4, 1 by 4, okay, it is 2.5. 2.5%. Again, these percentages, once you add them up, they must add up to 100%, which is, yeah, this plus this is 60 and then plus 40. Okay, so it also follows that if, let's say, someone tells me he has given me 3,000 grams of sodium hydroxide and asks me how much what is the amount of sodium in there, what's the amount of oxygen there, what is the amount of hydrogen in there in terms of grams, I'm going to be saying, I know that sodium in this, the composition, the percentage composition is 57.5%. So I'll be saying 57.5 over 100 of 300 grams. That's the mass of my sodium. Oxygen is 40%, 40 over 100 of the same 300 grams is oxygen. Hydrogen is 2.5 over 100 of 300 grams. And then I do my canceling there. I will get here is this 7.5 grams. I get here 120 grams. I get here 57.5, 57.5 by 3, 5, 31, 21, 22, 32, 17, then one decimal point, so 172.5. And again, if you add this one up, they should add up to 300. If you find they are not adding to that, yeah, then you have a problem. So if you know the molar formula, not molar formula, but relative formula mass, relative either molecular formula or of a compound or relative molecular formula, yeah, relative molecular formula of a compound, then you are able to come up with its percentage composition, and using the percentage composition you can be able to calculate moles or mass as per requirement. Let's have a look at this nice one. Mm, Consider the same product like the sodium hydroxide. Consider the same sodium hydroxide here. Okay. Uh, Suppose I ask you number of ions, number of sodium ions in 20 grams of sodium hydroxide. Okay, in this solution? Of course, the sodium hydroxide most of the time will be in a solution form. If I have a solution which contains 20 grams of sodium hydroxide, how many ions of sodium are in there, right? So let's come here. We know we know that its composition is in this manner. It's one sodium hydroxide. In it has one sodium which has combined with one oxygen ion and has also combined with the one hydrogen ion, like that. Okay, I've just broken them down based on the formula mass. So it tells me that 1 mole of this always contains 1 mole of sodium ions, 1 mole of oxygen ion, 1 mole of hydrogen ions. Oh, the one I'm talking about, it is here, one, and a one there. Okay, from this formula. Because of that, I want to know how many ions are in 20 grams. So here I'll come. I know the formula mass, we said it's what? 23 plus 16 plus 1, which becomes 40. I know previously, as we discussed, that 1 mole of anything will contain 6.0 times 10 to the power 23 particles of that compound, and in this case is sodium hydroxide, and it also must be have a weight of which is similar to its own formula mass, in this case 40. Okay, so in this case I'm dealing with a 20 grams. I want to know how many sodium hydroxide molecules that I have, because once I know this one, I'll be able to derive the rest of the quantities. Okay, and I'm going to cross multiply like that, and I'll get 20 multiplied by 6.0 times 10 to the power 23 is equals to x multiplied by 40. I divide by 40. I divide by 40 both sides to make x the subject of the formula. This one by 2, 1 by 2, 2 by 2, 1 by 2 is 3.0. So it means that in 20 grams, in 20 grams, in 20 grams, in 20 grams, I have 3.0 times 10 to the power 23 sodium hydroxide ions. I mean molecules. Okay. Now, I know this is how they divide. They go 1 mole and 1 mole of the sodium hydroxide will give me 1 mole of sodium. Let me just write one sodium ion and one oxygen ion and one hydroxide. One H ion. So if I have 3.0 times 10 to the power 23 sodium hydroxide particles, they will give me 3.0, because I'm just multiplying everything by 1 times 10 to the power 23. This is sodium ion, and the same number 3.0 times 10 to the power 23 or this oxygen, and the same number for hydrogen. So you can either do it like that. The other way you can do is, first of all, you calculate how many moles of each items you have. Let me get a different pen. Get you a different pen. Sorry. So okay, that way, and then I come here. because I want to do it slightly different ways so that you can get to the same, you can see you get to the same solution. I said that if I consider, I'll find that I have a sodium hydroxide, which when I analyze it, I'll find it has one mole of hydrogen hydroxide combined with 1 mole of oxygen ions combined with 1 mole of hydroxide ions as such. So when we said, well, if this 1 mole, if this is 20 gram is equivalent to how many moles? I do just the way we have been doing, that 1 mole of sodium hydroxide is equal to 40 grams. If I have 20 grams, how many moles is there? And you find it will be, after you do cross multiplication and you divide, to become 0.5 mole. Okay, so this one will tell me that I have 0.5 mole of sodium hydroxide. Now here I multiplied by 0.5. It means here I will do the same. I will have 0.5 mole of sodium hydroxide, 0.5 mole of sodium, 0.5 mole of oxygen ions, 0.5 mole of hydroxide, hydrogen ions. So I see that I have a 0.5 mole of sodium. So I'll come here and consider. Now I'm looking at the number of particles. So I know that 1 mole of sodium hydroxide, sodium ions, if it is really 1 mole, it must contain 6.0 times 10 to the power 23 ions. So if I am talking of 0.5 mole of the same, how many ions will it contain? I do cross multiplication and you see the answer becomes 0.5 times 0.6.0 times 10 to the power 23. This one will give you 3.0 times 10 to the power 23 ions of sodium. Okay, so it doesn't matter which way you choose, so long as you know what you expect to I mean where you want to end up, you really get there. I want to, considering the same hydroxide, let me work with something like aluminum hydroxide. Aluminum hydroxide, let's assume that it's there, aluminum hydroxide. If it is there, it will be written like that because aluminum has a valency of 3 and the hydroxide has a valency of 1. It's like that, and then the equation will be like this. So consider it's a formula mass. Consider its formula mass. I think aluminum should be 27 grams. This aluminum is 27. So its formula mass will be 27, and then we add 3 oxygens plus 3 hydrogens. Okay, this 27 plus 48 plus 3. Okay, okay. So once we add this one becomes 30 plus 48. That's 78 grams. So this one tells me that 78 grams of aluminum hydroxide will be 1 mole and will contain 6.0 times 10 to the power 23. So let me concern myself with, let's say, the same 78 grams. How many atoms of sodium are there, and of aluminum are there? How many atoms of oxygen are there? How many atoms of hydrogen are there, or ions in this case? So it will come like this. I know that 1 mole or 1 atom, I like dealing it in terms of mole. It's like this. This one, when you check it, it will contain 1 mole of aluminum ions, and 3 ions of hydroxide, but I want to break this one because I want to check the number of atoms of each type. So oxygen is there, and how many? Three hydrogen in such a manner. Okay, so when I come to here, I consider this is 78 grams. All right, so in 78 grams, this is 1 mole. Um, it will contain here, it will contain 78 grams will contain 6.0 times 10 to the power 28 aluminum, aluminum hydro, aluminum hydroxide, like that. So I want the number of aluminum in it, because you can see the ratio is 1:1, that aluminum hydroxide giving aluminum. If the equation is not balanced, we are not yet there. This is something else. And 3O and 3H. If I have 6.0 times 10 to the power 23, when I decompose them, I'll find 6.0 times 10 to the power 23 aluminum atoms in it. I'll find 3 into 6.0 times 10 to the power 23 oxygens. I'll find 3 into 6.0 times 10 to the power 23 hydrogens. That is in atom form. That will be like how the composition will be. All right. And you can try and work out for yourself the percentage composition of each, and try and find out if you did a certain mass of let's say hydrogen or aluminum hydroxide, how much of each quantity you would end up with. Right. Yeah. So far, I think so far so good. If I ask you something like find the moles of 112 grams of calcium oxide, you should be able to get what is the mass or moles of 112 grams of calcium oxide. Find the moles, percentage composition, and then mass of each kind of atom, each atom type in 112 grams of the compound. That one should be very easy. You can try it. You can try it. Okay. So I think we'll stop there, so that next time we continue to write the same thing, and especially the empirical formulas, because now we know a bit about the percentage composition. With the percentage composition, they are able to assist us to derive the simplest formula for this compound, which is called the empirical formula, and from there the formula of the compound itself. All right, so please look out for lesson 3.